My name is Tunç, and I'm going to start where Rafal left off from. And I'm going to introduce an image quality assessment metric that compares a distorted test image to a reference where the test and reference images can have different dynamic ranges. So image quality information can be helpful in various instances. For example, an image can be compressed until some disturbing compression artifacts start to appear. Similarly, image processing algorithms performing the same task can be compared to each other by assessing the quality of their results. On the other hand, global illumination algorithms can be steered by the image quality information, and a speed up can be achieved by rendering only those details that affect quality. But how does one assess image quality? At the receiving end of the image information are humans, so therefore the most reliable way of assessing image quality is through subjective experiments. These type of experiments involve a group of subjects, and in these experiments subjects are asked to compare a group of distorted test images with respect to a reference, and the task is to rate the quality according to a certain scale. But the downside of this method is that it requires a lot of subjects in order to be accurate, and each of the subjects has to spend a considerable amount of time at each trial, making the overall process very costly. On the other hand, one can mathematically define image quality and perform image quality assessment through so-called image quality metrics. This method is much faster compared to the subjective methods, but especially when simple metrics are used, the predictions are not as good as the subjective methods. So in this example, the mean squared errors, possibly the simplest quality metric, predicts the three distorted images to be of the same quality. But the luminance shift depicted in the rightmost image is barely visible, whereas the other two are visible. We can do better by modeling the human visual system and detecting visible differences between images. In this example, the metric output is shown in so-called in-context distortion map, where the image luminance is shown in grayscale and distortions are color-coded. So at this time around, the metric detects no distortions for the luminance shift, but it detects distortions everywhere for random noise. But a visible difference between the reference and test images does not necessarily indicate a degradation in quality. We can capture this fact by detecting distortions in image structure. And in this context, an operation like the contrast enhancement does not degrade image quality because it does not alter image structure. Whereas on the other hand, for example, adding random noise does change image structure by introducing new details to the image, and therefore degrades image quality. So to sum up what I said so far, simple quality metrics do not explicitly model the human visual system, and they do not consider image structure. However, human visual system-based metrics do explicitly model the human visual system either for a limited dynamic range or the full dynamic range, but they are still based on the visible differences, and they do not consider image structure. On the other hand, structural similarity-based metrics do consider image structure, but their calibration is challenging due to the abstract model parameters. So our metric can be considered as a hybrid between the human visual system-based approach and the structural similarity-based approach, in that we model the human visual system, but in the end we detect structural distortions in the image. Our main point of focus is, hence the name of the paper, enabling a dynamic range-independent image quality assessment. Namely, we would like to handle the case where the test and reference images have different dynamic ranges. This is not a trivial problem. As you can see in the slide, a human observer can easily see that the HDR and LDR image are from the same scene. But if we compare their luminances, they are very different. And this difference due to the dynamic range is far more complex than a simple luminance shift or an increase in contrast, and far larger in magnitude. So the outline of the rest of the talk will be as follows. First, I'm going to talk about the human visual system model that we use to convert image luminance to multi-resolution, multi-orientation human visual system response scaled in so-called just noticeable difference units. Next, I'm going to introduce a set of three quality measures, distortion measures that we use to detect distortions in the image structure. Next, I'm going to compare our approach with previous approaches and then list some applications. But let me start with the human visual system model. So here you can see the main building blocks of our model. The input to our model is image luminance, and we simulate various mechanisms of the human visual system, like the scattering of light in eyes optics, the nonlinear perception of luminance, spatial frequency dependency of contrast sensitivity, and the frequency and orientation selectivity of neurons in the visual cortex. And now I'm going to go into a little bit more detail for each of these mechanisms. So first, light scattering. Light gets scattered after entering the eye due to the optics of the eye. And that's why in the presence of a very bright light source, the visibility of details decreases significantly around that bright light source. This effect is not as common in the so-called low dynamic range, that is the dynamic range of a typical CRT or LCD display. But it has a significant effect on our perception of HDR images. So in this example, you can perhaps you can see the text on our paper and maybe even read the largest printed words, although I don't think so. But if I turn on the light, then the visibility of the text decreases significantly due to the glare, due to the visibility glare caused by the bright light source. This effect we model by using an optical transfer function in the frequency domain that is somewhat like a Gaussian, and it depends on the pupil diameter and the spatial frequency. The next mechanism that we simulate is the nonlinear perception of luminance. We model this effect by transforming image luminance to the so-called just noticeable difference space due to Montiuk et al. This space has a property that adding or subtracting the unit value results in a barely noticeable difference in image contrast. Another mechanism is the spatial frequency dependency of contrast sensitivity. This effect can be easily observed on this Campbell-Robson chart, where along the horizontal axis the spatial frequency increases and on the vertical axis contrast decreases. The point of this chart is to see the minimum luminance required to see a certain spatial frequency. And although the exact thresholds will depend on your viewing distance, which in turn depends on where you are sitting in this room, I hope you can still see that higher contrast is required to see the very low and very high frequencies, whereas the middle frequencies are visible even at very low contrast levels. Finally, it is widely accepted that the image information registered by the retina is transmitted through a set of visual channels, each of which carrying different spatial and temporal frequencies, colors, or orientations. Cortex transform is just one of the models that models the frequency and orientation selectivity of the neurons in the visual cortex. As a result, the image is decomposed into 6 frequency bands, each of which have 6 orientations, except the lowest frequency band that has no orientations. So now I'm going to introduce a set of very simple but yet very powerful distortion measures that we use to detect structural distortions in the image. As opposed to the traditional approach based on the visible contrast differences, our metric is based on the visibility of contrast in the test and reference images. So in this case, contrast is visible in the reference image, but in the test image it becomes invisible. We call this type of distortion the loss of visible contrast. Clipping is one of the many operations that generates this type of distortion. So in this example, the bright sky region of this image is clipped, and as a result, we cannot see the clouds at that region anymore. So our metric successfully detects loss of visible contrast in that region that is shown with the color green. Amplification of invisible contrast is the exact opposite case, namely when the contrast is invisible in the reference image, but it becomes visible, it is boosted somehow above the visibility threshold in the test image. So in this example, we compare an 8-bit image with its 4-bit quantized version. As a result of the strong quantization, contouring artifacts start to appear. And our metric successfully detects the amplification of invisible contrast along the newly appeared contour lines. And this type of distortion is indicated by blue in our visualization. Finally, contrast can be visible in both images, but its polarity can be reversed. So this type of distortion we call reversal of visible contrast. So it is worth noting that this measure is somewhat more artificial compared to the previous two. In fact, to generate this test image, I locally reversed the contrast in the reference image at some frequency bands, and our metric responds accordingly and reports reversal of visible contrast in that area. But although somewhat artificial, detecting contrast reversal has still some value because this type of distortion appears as a byproduct of many image processing algorithms, including some tone mapping algorithms that are known to generate halo artifacts. It is also worth noting that in the case that there's an increase or decrease in contrast, but at the same time the contrast is either visible or invisible, in both test and reference images we do not detect any distortions. Although these cases may correspond to a visible difference between the two images, they do not affect image structure, and therefore we do not care about them. So we calculate the detection probabilities of all three types of distortions at each visual channel, and then sum up these probabilities through a standard probability summation formula to generate three separate distortion maps, one for each type of distortion. The opacities of these maps are modulated as a function of the detection probability of those distortions. We combine these maps, these individual maps, with the image luminance to generate the final distortion map. Now, in this incarnation of our visualization system, if there are overlaps, if there are image regions where multiple distortions overlap, we only show the one that has the highest detection probability. But we also have a custom viewer tool where one can manually adjust the opacities of different distortion maps, which enables a finer analysis in regions of overlap. Okay. So now I'm going to compare our metric to previous approaches, namely two previous metrics, SSIM and HDR-VDP, which are well-cited, well-known quality metrics. And to do that, I'm going to use the following tests set. First, an HDR reference, then a low dynamic range reference that is generated by compressing the contrast of the HDR reference, and then two test images that are generated by adding local Gaussian blur to the reference images. So in the first case, both reference and test images are high dynamic range. So to prevent any confusion here, the outcome of both HDR-VDP and SSIM are functions of distortion magnitude. And we use HDR-VDP's visualization code for both metrics where different colors indicate different levels of distortion. But as I explained earlier, in case of our metric, different colors indicate different types of distortions. Having said that, in this case, all three metrics successfully detect the distortions caused by the local blur. Similarly, in the case where both test and reference images are low dynamic range, all three metrics successfully detect the local distortion, although somewhat different in magnitude. But interesting happens when the images have different dynamic ranges. So in this case, the large magnitude of differences due to dynamic range saturate the distortion maps of both HDR, VDP, and SSIM, and it occludes the distortions caused by the local blur. Our metric, on the other hand, detects an overall amplification of invisible contrast, which is expected since the test image has higher dynamic range than the reference in this example. But we can also clearly see the distortions caused by the local blurring. Similarly, in the case where the test image is LDR and the reference is HDR, our metric reports an overall loss of contrast because this time around the test image has lower dynamic range. And likewise, the distortions in the blurred regions are still visible. Another advantage of our metric is that we do not only detect the existence of distortions, but we also detect their type. So in this example, the responses of HDR, VDP, and SSIM are very different in magnitude. But each metric's response to blur and sharpening are very similar to an extent that we cannot differentiate between those two types of operations. On the other hand, our metric detects the contrast amplification and reversal due to sharpening and the contrast loss due to blurring. So our metric gives some insight about the image processing algorithm that is used to generate the test image. So in the final part of my talk, I'm going to talk about some applications of our metric. Probably the most obvious application of our metric is to evaluation of tone mapping operators. Tone mapping operators take as input high dynamic range images and they compress its contrast and return a low dynamic range image. In this example, the bookshelf region of the reference HDR image is not as dark as it is reproduced by pattern X operator, and therefore our metric detects a loss of contrast there. But the same region also doesn't have as high contrast as it is depicted by Fatals operator, and our metric responds accordingly. So in a similar fashion, we can also compare other tone mapping operators. And again, similarly, our metric can also be applied to evaluation of inverse tone mapping operators. These operators take as input low dynamic range images, and they stretch the contrast of the low dynamic range image and generate a high dynamic range image. So as we can expect from this type of operations, our metric detects an amplification of invisible contrast in some image regions. And finally, we can compare the simulated appearances of an image on displays with different capabilities. We model the displays by measuring their response curve using a luminance meter and converting image luminance to display luminance. So in this example, we can see that the prototype HDR display is perfectly capable of reproducing most of the details of the reference HDR. But the high dynamic range of the image exceeds the capabilities of even a high quality medical display. So in this case, we start to see some contrast amplification in dark areas and some contrast loss in bright areas due to clipping. And finally, a device as limited as a cell phone display simply fails to reconstruct most of the details of the HDR image. So in summary, I presented a dynamic range independent image quality metric. And our approach is a hybrid between the human visual system-based and structure-based metrics. The main advantage of our metric is that it can compare images with different dynamic ranges. And we do not only detect the existence of distortions, but also their type. I presented applications to evaluation of tone mapping operators, inverse tone mapping operators, and display comparison. And finally, some limitations of our work is that we consider only image luminance, and our models are strictly threshold models. So as future work, it will be interesting to extend our metric to color and to include super threshold models. And finally, please visit the website of this project, where you can find some pre-generated sample maps. And we also recently implemented a server where you can upload your images and run our metric for yourself and see the result for yourself. Thank you very much for your attention.
Thank you, Tunç. So your classification of contrast distortion operators, reduction, reversal, amplification, seems to be very useful. Can you think of some other ways of exploiting it and maybe other applications?
That's an excellent question. Actually, one thing that we can do with this kind of classification is that, for example, in case of tone mapping, one goal of tone mapping might be to reproduce as many details as possible. So in this context, for example, an amplification of contrast cannot be considered as distortion. So by classifying these different types of distortions, we can, for example, only care about loss of contrast, but not amplification of contrast, which is not possible if you have only one type of distortion.
And also notice that although your operator is quite useful in your classification, you're not looking at the loss of sensitivity due to similar frequencies, visual masking, effectively. Do you think you can deal with that situation?
Visual masking is is an effect of the human visual system, basically, which we see at suprathreshold level. But if you look at our distortion measures, they are basically near the threshold where visual masking doesn't have a significant effect or any effect at all. So we can have a model of the human visual system, but it won't change the results. So it will be just some additional computation in our pipeline. So therefore, we don't have visual masking.
But will your classification still work in presence of visual masking?
I'm sorry?
Will your classification still work in presence of such?
Yes, because visual masking will only change the value or the magnitude of the human visual system response, and the classification criteria will be still similar.
Questions?
Paul Hofman, NXP Semiconductors. What you presented is what I think you call in literature a reference metric, right?
Can you please speak loudly?
Yeah. What you presented is what I think the literature is known as a reference metric as compared to a no reference metric. Did you try this on a compression case? So to have the original and the compressed version, and to have a, say, good assessment of the level of annoyance and artifacts in the image. Of course, I think the most relevant case of video processing in TVs and mobile displays at the moment.
We did some informal studies on that, but I mean, not a structured study. But in general, this metric can detect any type of distortion, be it compression artifacts or some other. But we did not produce any results that I can report right now.
I would be very curious if you have any results on that. Okay, thanks.
Can you tell us some more? Can you tell us about the execution time? And given that you can implement a lot of those transforms on, say, GPUs, are there ways to speed up this transformation?
Right. The running time, of course, it depends on the image size. But if we have like a 512 by 512 image, then it usually takes 15 to 20 seconds, roughly. And most of the time, or most of the processing goes to Fourier transform and inverse Fourier transform. So if we can find a better way of doing those transforms, or faster way of doing those transforms, then it would speed up our pipeline as well, including like doing those things on GPU.
Question?
Have you compared your model to how people would rate the images?
Can you speak loudly?
Have you compared your model to subjective ratings of the image differences?
Right. We did a validation study consisting of a set of psychophysical experiments, which are explained in detail in the paper, but I did not have time to present them. But
thank you.
But we did such a study.
Let's thank our speaker.